In this lesson, we will learn about universal set. A universal set is defined as a set which contains all the elements of a problem which are under consideration. So what do I mean by that? For example, A equal to x belongs to z such that minus 10 less than or equal to x less than or equal to 10. So this is a set where all the elements of the set are integers and they lie between minus 10 and 10. So here in this problem, all these elements belong to a universal set of integers called z. So in this problem, z is the universal set and A is the set which contains numbers from minus 10 to 10 from the overall universal set z. Similarly, all the students of Trinity School who scored greater than 500 marks in the SSC exam. So here in this set, all the students of Trinity School are a part of a universal set, which is all the students in that school. And the set under consideration over here is only those particular students who have scored greater than 500 marks in the SSC exam. So in these two examples, Z and all the students of Trinity School are the universal sets. Next we will learn about empty set. A set which does not have any elements is called an empty set or a null set. Let's look at some examples. Here in the first example we have defined the set A as x belongs to n is all natural numbers, where x square is less than 0. There is no natural number which will satisfy this condition. So this set is called an empty set because there are no elements in that set. So if you write this set in the form of a roster form, A would be equal to an empty set. An empty set is represented as open brace and close brace with no elements in it in the roster form. Similarly, all the people who are born after the year 2020, there is no one who is born after the year 2020. So again, that set is an empty set with no elements in it. So these are some of the examples of empty sets. An empty set is represented either by using this open brace or closed brace with no elements in it, or using the symbol phi. As you can see here, you represent an empty set with the symbol phi. Next we will talk about singleton. If a set contains exactly one element, it is called a singleton. For example, look at the first set. A equal to A belongs to capital N, all natural numbers, such that A greater than or equal to 4 and A less than or equal to 4. The number that satisfies this condition is 4, and it is only one element that satisfies this condition. So if you write this A in the form of a roster form, it will be A equal to 4. So this is a singleton. Similarly, B equal to X. It has only one element, which is X. So B is also a singleton. Next we will talk about equality of sets. Two sets are said to be equal if and only if they have the exact same elements. Let's look at some examples. The first one, here we have a set A equal to 1, 2, 3, 4 and set B is 3, 4, 2, 1. If you observe closely, they are exactly the same numbers, just the order of the numbers is different. So these two sets are equal because they have exactly the same numbers. So A equal to B. Okay, next let's take another example. Here A equal to 2, 4, 6, 8. This is represented in a roster form, and set B is A belongs to capital N, which is natural numbers, such that A is an even number less than 10. So if you write this in the form of roster form, you see that A is an even number less than 10. So let's start with the first even number 2, next one is 4, next one is 6, next one is 8. So 8 is the last even number which is less than 10. So if you observe closely, A and B are exactly the same. The last example, A equal to 5, which is a A is an empty set, and B equal to there is a phi inside the braces. This is not the same as the empty set. This is a set which contains an element which is an empty set. So if you write these in the form of roster form, the first one, A is represented as A equal to open brace close brace, and B is represented as, so if you observe closely, A is not equal to B. So you must be very careful when determining if two sets are equal. The best approach is if you have two two sets, one in a roster form and another in a set builder form. I would suggest you convert both of them into roster forms and then do a matching to see if A and B exactly have the same elements. Next we will learn about subsets. If A and B are two sets such that every element of A belongs to B, then A is a subset of B, and it is represented as A and this symbol here with an equal to B. But if A is a subset of B and A is not equal to B, then A is called a proper subset of B, and it is represented as A subset B without the equal symbol. Let's take some examples. The first one, A equal to 1, 2, 3 and B equal to 1, 2, 3, 4. If you observe, every element of A is contained in P. But A and B are not equal because B has an extra element 4. So A is a proper subset of B, and that should be represented as a proper subset B. The second example, A equal to 1, 2 and B equal to 2, 1. Both the sets are identical, but the numbers are reversed. Order of the numbers are reversed. So every element of A is contained in B, and they are equal as well. So we call this as A subset B, and we have to represent a subset with a symbol and a equal to. There are two theorems that are important to remember. The first one is an empty set is a subset of every set. Similarly, a set is a subset of its own set. Let us now learn about power set. A set of all subsets of a given set A is called the power set of A, and it is denoted with P of A as shown here. So let us look at some examples to understand what do we mean by this. So consider the set A equal to 5. It has only one and only one element. So this is a singleton set. So what are the possible subsets of this set? We know that empty set is a subset of every set. So that is the first one. And the second one is that there is only one element. So and we also know that every set is a subset of its own set. So just we have to write the 5 in the braces, which is nothing but the set A. So there are only two subsets of this singleton, pi and the set with the element 5. Let's take another example where we have actually two elements now, x and y. So let's look at what are the possible subsets of this set. So again, every empty set is the subset of every set. So begin with that, and then we can have a subset of B which will have just the element x or just the element y, or both the elements x and y, which is again the set B itself. So there are four different subsets of the set B. So over here we have 2, and over here we have 4 subsets. So P of B with a power set of B contains 4 elements as shown here. Now let's take another example where we have 3 elements in the set A, B, C. Now again let's start with the pi, which is the empty set, and then it can have just one element A, B, C. We can have a combination of two elements, which A and B, B and C, A and C, and again at the end the set itself, which is A, B, C. If you count here, we will have 8 subsets. The power set C is a set of 8 subsets of the set C. If you observe closely, when a set has one element, we have 2 power 1 elements in the power set. Similarly, when the set has two elements, we have 2 power 2 subsets in the 2 power 2 subsets. So the power set will have 4 elements. Similarly, when we have 3 elements in the set, we have 2 power 3 elements in the power set. So we can say that if a set has n elements, then power set of A will have 2 power n elements.